Write a function is solvable maze that takes in a maze and returns true if the maze is solvable and false otherwise. So here, the maze that goes into our function is a list of strings, and inside the strings there are certain symbols. And here, S means the starting position of our player, X means the end, dash means a road in which the player can exist in, and hash means a wall in which the player cannot exist in. So here are some rules of this maze. So we assume that S will always be on the top left, such as here and here. S can only move one step at a time, and S can only move in 4 directions, up, down, left, and right. Also, S can only land on dash characters and not hash characters. And here, S wins if it reaches X. So here, a maze is solvable if S can reach X eventually. So here, let's take maze 1 as an example. So in maze 1, we start at S, and we can go downwards, and we can downwards again, and we can go downwards, and we can go right, 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 and eventually we'll reach X. So here, maze 1 is solvable because S can eventually reach X. So now let's take a look at maze 2. So we start at S, but no matter how we move, we cannot reach X because we are blocked by these hash walls. So in this case, maze 2 is not solvable. So do pause this video and take some time to give this a go before taking a look at the answer. So here, let's first define is solvable, and it takes in a maze, and let's add in a pass at first, and here, let's add in a maze. So before we jump right into our function, let's figure out how our function will work. So here, let's first draw our maze first. So we have S dash hash dash 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 hash dash dash, and then we have dash hash triple dash 4 dashes and X. So here we know that S can eventually reach X if it goes in this direction, and that this is going to be solvable. So here the first step would be to decide how we want to represent our maze. So when we start here, we are actually at coordinates 0 and 0. And when I say 0 and 0, this is the row number and this is the column number. And this makes sense because our maze is actually some sort of 2D list. So similarly, this is going to be row 0, this is going to be row 1, this is going to be row 2, and this is going to be row 3. And here, this is going to be column 0, this is going to be column 1, column 2, column 3, and column 4. So here we have row 0 and column 0, and that's why this one is 0, 0. And if we take a look at this one, this is going to be row 0 and column 1. So this is going to be at coordinates 0, 1. And if we go down instead, this is at row 1 and column 0. So this is going to be 1, 0. So here, each of these points on our maze actually has a coordinate. And with this in mind, we can actually start from coordinate 0, 0, and we search up, down, left, right repeatedly. So from 0, 0, we are going to search 0, 1, and from 0, 1, we can search 0, 0, this one, and this one. However, we do need to take note that we cannot exist on hashes. So eventually, we are going to search here, 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 here. And if we reach X, we know that this is going to be solvable. However, if let's say we replace this with a hashtag, we are only going to be able to search from here to here. And if this is the case, we know that this is not solvable. So with this in mind, let's get back to the code. So firstly, I'm going to create a set scene and a list queue. So here, queue will start with 0 and 0 because we always assume that S will be at the top left corner of our maze. And next, while the length of queue is more than 0, or in other words, as long as there is something in queue, our while loop will keep running. So the first step here would be to take out the first thing in queue. So queue.pop 0. So here, the pop method will take the first thing in our list, it will remove it from our list, and then it will assign it to something. So let's put row column is equals to queue.pop. So this is the first step. And next, let's add it into scene. So row, comma, column. So the purpose of adding it into scene is such that we do not search a certain point twice. And afterwards, we check if we are on X. So if we are actually on X, we know that we have reached X and that this maze is solvable. So we return true straight away. So if maze row column is equals to X, we simply return true, and that will be the end of our function. However, if we are not on X, then it is time to search our neighbors. So let's say we are on S, and the neighbors would be here, which happens to be 0, 1, and here, which happens to be 1, 0. So here we add our unseen and valid neighbors. So for a neighbor to be added back into the queue for further searching, it has to fulfill two conditions. Firstly, we shouldn't have searched it before, and secondly, it has to be valid. So here, for AB in list, and here we are going to have 4 tuples. So here, because we already have a certain coordinate, we have to find the coordinate that is on top, below, left, and right of our current coordinate. So this is how we are going to do it. So 0, 1, 1, 0, this is going to be 0, negative 1, and this is going to be negative 1, 0. So here, new row is equals to row plus A, and here, new column is equals to column plus B. So here, I'm just simply going to print this first. And for now, let's test this. Is solvable, and we pass in maze. So note that we are currently at 0, 0, and let's check out the 4 coordinates that are generated from this. So here, I'm going to have 0, 1, 1, 0, 0 minus 1, and minus 1, 0. And here, because we are at the corner, we are going to generate these 4 points. This point, this point, this point, which happens to be outside of the maze, and also this point, which also happens to be outside of the maze. So these two are not valid, and we have to write some code to get rid of them. So here, if not valid coordinate, new row, new column, and maze. So essentially, if this coordinate is not valid, we continue and ignore this certain new row and new column. So right now we have to write this function above here. So define valid coordinate, so new row, new column, and maze. So here, neither row nor column can be negative. So let's do that first. So if new row is less than 0 or new column is less than 0, we simply return false. Because if anything is negative, it cannot be a valid coordinate. And next, we have to take care of the out of bounds error. So here, let's simply use a try except. And if anything goes wrong, we know for sure that this is not a valid coordinate. So we return false. And here we have symbol is equals to maze, new row, and new column. And for this symbol to be valid, it can only be either a X or a dash. So we return symbol in X or dash. So for now, our valid coordinate is done. So let's try this again. So new row and new column. And so let's print this again. And here we will only generate our valid coordinates. So here notice that 0, minus 1 and minus 1, 0 are gone now. So let's get rid of this and let's move on to the next step. So here we have tested for valid neighbors, but we haven't tested for unseen neighbors. So if new row and new column in scene. So once again, scene is our set here, and whatever we have searched before, we simply add it into scene. So if this one is already in scene, we do not want to do double work, so we simply continue to. And if it fulfills both of these conditions, we can add them to queue. So queue append new row and new column. So this will be the process of searching every single searchable coordinate on our maze. And at the end of our function, if we do not find any X, we simply return false because we know that X is just simply not there. So here, let's print is solvable maze and let's run our code. So once again, this is our maze and we are expecting this to be solvable. So this should give us true. And here we have it, true. However, if we replace this with a hash, it should give us a false now because S cannot reach X by any means. So now this should give us a false. And here we have it, a false. So here, if you are new to graph search, let's take a look at how this actually works. So firstly, let's change this back to a dash. And similarly, let's draw out our maze first. S dash hash dash dash. And next we have dash dash hash dash dash. And we have dash hash dash dash dash. And we have dash 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 x. So here, we start with 0, 0, which happens to be S here. And since this is not an X, we do not return true straight away. And we search its valid neighbors. So here, the valid neighbors happen to be this one and this one. So this one is going to be 0, 1, while this one is going to be 1, 0. So here, once again, we start with our queue, 0, 0. And in the first iteration, we cancel 0, 0, and we add in 0, 1, and 1, 0. So next, let's say we search 0, 1 first. So we get this out, and we search its valid neighbors. So its valid neighbors are going to be 1, 1 only. So this is going to be 1, 1. So we might want to search this, but this is actually a hash, and this is not a valid neighbor, so we do not search it. So next, we add 1, 1 back into our queue. So we are going to have 1, 1. So none of these are X, so we just continue doing what we are doing. So next, we search 1, 0. So we take this out of the queue, and 1, 0's valid neighbors are 1, 1 again, which is already in our queue, and we are going to get this. So this is going to be 2, 0. So let's add 2, 0 to our queue, and next we are going to search 1, 1. So 1, 1 has no other unsearched valid neighbors, so nothing happens. And once again, from 2, 0, we get 3, 0. 3, 0. So 3, 0 gets added into the queue, and 2, 0 disappears. And from 3, 0, we get 3, 1. So once again, we get this out of the queue, and now we are going to have 3, 1. And once again, from 3, 1, we are going to get 3, 2. And this disappears, and we add 3, 2 into the queue. And at this point, we now have 2 paths to go. So from 3, 2, we have this and this. So this is going to be 3, 3, and this is going to be 2, 2. So once again, 3, 2 disappears, and now we add 2 things into the queue. So they are going to be 2, 2, and it's going to be 3, 3. So let's say we search 2, 2 first. So from 2, 2, we are going to get 2, 3. So this is going to be 2, 3. So we get rid of 2, 2, and we add 2, 3 into our queue. And next, let's search 3, 3. So from 3, 3, we are going to get our X. So 3, 3 disappears. However, because we have already reached X, so we return true at this point. And from here, we know that our maze is solvable. So none of these other things are going to be searched. However, let's say we replace this with a hash. So if we start searching from 0, 0, so we are going to go 0, 1, 1, 0, 1, 1, 2, 0, and from 2, 0, we do not have any other valid coordinates to search. And at this point, our queue will eventually become empty, and will return false at the end of our function. So once again, thanks for watching, and hopefully this was clear and easy to understand. See you in the next one.